the mechanisms with which a given reaction can occur. Okay, so for instance, there's this example that has been given here, the combustion of methane in oxygen. So when methane is burnt in oxygen, it produces carbon dioxide and water. Again, if we burn gasoline, which is kerosene, this is a constituent of kerosene. In oxygen, this is what is produced. Okay, all these processes are happening. And when we look at them, we might think, oh, they are one and the same. But in the actual sense, there might be minor things that can bring about a difference in their reaction by looking at factors that are actually affecting these reactions. Or the reactions may be the same, but the rate at which these reactions are going to happen is going to be different. Why? This molecule and this molecule are different. Since they are different, the reactions are also going to be different on that particular basis. But we're going to look at that further. Now, when we are doing kinetics, what it is that is important for us to understand here is that the rates of a chemical reaction are very important. So therefore, we are going to start looking at what the rate of a reaction actually is. All these studies here is actually explaining thermochemistry and how it is interconnected to electrochemistry and how it comes to kinetics, but we don't need to start looking at all that. So let's just straight away go to rates of a reaction. So the rate of the reaction is actually the change of a particular species with time, like I tried to explain yesterday. So every time you are going to use per time for the unit for rate. So rate here, they're saying, is usually expressed in units of moles per liter per time. Now, mole per liter, this part here, mole per liter is the same as molarity, which is molar, which is concentration. So in short, the rate reactions, the rates of reactions are going to be expressed in molar per unit time. So time factor is not going to be restrictive. Like there's supposed to be a standard time. There is no standard time factor. You are going to be using whatever time you are using for your measure, as long as it is time. Meaning you can measure the rate of the reaction per second. You can measure the rate of the reaction per minute. You can measure the rate of the reaction per hour, or you can do that per month, per week, per year, as long as you are looking at time. And all these factors, all these variables were just from looking at what? Time variables. Okay. So all these variables, like I've said, time variables, and therefore can be used in okay, so these time, the time variables, I've encountered a lot of people trying to say, no, sir, we are supposed to use per minute, per second for the time. We are supposed to use per second for the time. No. This is not restrictive to time. Okay. Whatever time you use, you're going to use that. And then one, so we can now find this rate when you look at a given chemical equation. For instance, this equation here, where carbon is reacting with oxygen to give carbon dioxide. When we use this particular reaction and we want to find the rate at which this reaction is happening, we can use any one of these for the calculation of the rate. It's not restrictive to only one at this particular point. So you can study the rate of this reaction with respect to carbon. So at what rate is carbon being consumed? Because it's a reactant, it is going to be consumed. Or you can look at what rate is oxygen being consumed, because it is also a reactant. Or you can look at this particular reaction at what rate is what? Carbon being produced. Irrespective of which one of these you're going to pick up to look at your rate of the reaction, any one of them is going to give you an answer that is that is the rate at which the reaction was happening. Irrespective of which one you get, the rate is going to be the same when you use it for your calculation. So what we actually do is we just tend to follow. Okay, you have this concentration at this particular time, then you have another concentration at another given time. So in this given time, how much has changed? At what rate is this happening? So that is how we measure the rate when it is being calculated. So to describe the rate of the reaction, we must determine the concentration of a reactant or product at various times as the reaction proceeds. So this is what I'm just from explaining. And then devising effective methods for this is a challenge to chemists who study chemical kinetics. That is, we can move from that. And then this is an example of a device that can be used. Okay, so this is how mostly reactions are studied. So this is, and then it plots the graph on itself and stuff. This is how you're going to be collecting data. But this is not the only method that you can use. You can actually go by the concentration method. After a given time, it's just that you guys are not going to do that particular part of chemistry. You have the syllabus has changed. I would have told you that next year there is a reaction that there is a lab that we do in analytical chemistry where we measure the rate of the reaction. This particular concept we are learning here, second year we actually do it, where the reaction is going to start happening. After a given amount of time, you get an amount from your reaction vessel, you measure the concentration, you record. After a given time, at that particular time, you get again another volume, you measure the concentration just like that until about 45 minutes, after which you stop, and then you use that to determine the rate of the reaction. What order is it? What is the rate? And at the end of the day, you tend to tell us the mechanism by which the reaction is going to happen. No. Actually, it's even in organic chemistry, not analytical. It's in organic chemistry where we do this same thing that we are doing here, but in the lab setup. Okay, so let us look at the reaction of nitric pentoxide. So dinitrogen pentoxide can decompose to give us nitrogen dioxide and oxygen. So what does this actually mean? This means that for every 2 moles of dinitrogen pentoxide gas that reacts, a total number of 5 moles of gas is formed. This 5 moles is broken down 4 for nitrogen and 2 for oxygen. Meaning, if it comes to studying the rate of the reaction, these coefficients you are seeing here, these 2, these 4, and there's 1 in front of oxygen, should be considered in your rate calculation. So what we're going to do, or what you're supposed to know, is that once we have measured the changes of the concentration of reactants or products with time, how do we describe the rate of the reaction? So we consider hypothetically A plus B giving us C plus D. If this is what we have and we want to measure the rate of the reaction, the rate of the reaction is going to be given by, I've not seen an equation given. So you can write an hypothetical equation, a small letter A plus B to give you C, to give you C. Okay, so hypothetically, you can write AA plus BB to give you C, C and D. Okay, so this, when you want to calculate the rate of a reaction is okay. So here, let me share a different. Let me share. Did I write something? Okay. Let me try to share something that I was writing up when I was trying to go through. Okay, so the rate of the reaction is given. Let me try it. Okay, so I think I can still use this for showing you the rate. It's there, so the rate of the reaction. So the rate of the reaction is going to be equals to, when you are looking at the reactant part, when you're looking at the reactant, you're going to say rate is equals to negative, okay, negative delta or negative change, that triangle symbol, this symbol here, actually, yeah, this is what I'm trying to explain here. When you are looking at the reactants, since the reactants are disappearing, you are starting with a large amount and then it is going to a smaller amount. When you subtract these two, they will give you a negative. Okay, so say you are starting with 25 grams of A. Okay, so you start with 25 grams of A, and then after 10 minutes, you measure how much mass of A you have remained with. Since A is a reactant, so you're going to say you have remained with, say, 15 grams after 10 minutes. When you are finding the change in the concentration of A, you're going to say final minus initial. So the final in this case is 15. Your initial is going to be 25. When you subtract, the answer is going to be negative 10. But you don't want your answer to be negative because there is no negative rate. Now, for you to compensate for this negative that comes out of the change subtraction, every time you are measuring the rate with respect to reactants, the rate equation should have a negative sign. So you're going to write rate is equals to negative change, like the way they've written here. So if this is the equation that you have and you want to measure the rate with respect to A, it is going to be negative change of A divided by the change in time. Okay, that is how you write it. If you are measuring with respect to B, you are going to write the negative change of B over change in time. So all those equations we are writing are what? Rate equations. Now, this is with respect to reactants. If you are measuring the rate with respect to products, you have to do the calculation. The equation is the same and stuff, but this time, since it is the product, and the product increases from a smaller number to a larger number, because at the beginning of the reaction, mostly, you won't even have any of the products. The products will start being produced in solution. So this amount increases, and therefore there's no need for you to include a negative sign. So when it comes to writing the rate with respect to products, you write them as positives. So rate is going to be equals to, so for instance, if C is your product and you want to measure the rate of this reaction with respect to C, you're going to say change in C is divided by change in time. So this is the rate of change with respect to C, or change in D with respect over change in time. So this is positive because these are being produced in solution. Okay. So every time you measure this, this is what is going to happen. But then here, one other thing we have not put into consideration is the coefficients, the ratio in which these reactions are happening. So if, like they've explained here, on other reaction takes place, no other reaction takes place, the changes in the concentrations are related to one another. Okay, if this reaction is just happening like this and nothing else happens, all these reactions are related to one another. So for every, now this is the relationship that is there, for every one, or for every A moles, that is the moles of A, okay, decrease, B must decrease by B. Okay, meaning these coefficients here, if say this was 2 and this was 3, it will simply mean that for every 2 moles of A that you consume, 3 moles of B are supposed to be consumed in the same reaction. So this is the relationship that is there. And then for every A, or if we use numbers, say 2, 3, and then 1 here or nothing there, every 2 moles of A that are consumed, 1 mole of B is produced. Now, these can be used to bring about a relationship in the reactants and the product. So every species in a given equation, as long as this particular equation happens as is written and nothing else happens in this particular reaction, what you're going to understand is that this is going to give you a relationship that is in this particular form. So the relationship is going to have the coefficients. So what we do is we have to reduce all of these to 1 more of each one. So if A is a variable that you do not, it's other than 1, this is going to be 1 over A, and then you multiply it by the change in concentration of that for you to have the same rate throughout. So for the rate to be the same throughout, this is what we're going to say here. 1 over A, so 1 more reaction over A more of A times the rate of decrease of A. So the reaction is going to become a fraction. So this becomes 1 over A, and then, so this equation you are writing here. Now, if you are writing the relationship that is there, it is going to be rate is equals to 1 over A, and then this. So 1 over small letter A, no need for you to write these. No need for you to write that. There is no need for you to write this. All you have to write is 1 over A. So remember, it's a reactant. So minus 1 over A, and then change in concentration over T. So these combined, without these words, just this and that combined. That gives you the rate of this particular reaction. So you can now connect all these by one equation by saying rate is equals to 1 over A, and then multiplying it by the change in A over change in T. Then you say equals minus 1 over B, change in B, change in concentration of B divided by change in time. So to these expressions, like this expression I have here, negative change in T over time, the only thing I'm doing is you put in front before the delta, this symbol, you put 1 over A, and then you write this, and then you put an equal sign, 1 over minus 1 over B, and then you write this. So you put minus then 1 over B, then you write change in the concentration of B divided by time. Then again you say is equals to 1 over C, and then you write change in the concentration of C divided by time as it is here. And then you again put equals to 1 over D, and then you write this. So that simply means you have a relationship that connects all the species that you have in this particular reaction. So that equation you've written connects this, meaning I can give you the rate at which A is being consumed, and I can ask you to calculate the rate at which D is being produced. You'll be able to do that because you have that equation that is equating the two. So all you have to do is get whatever it is that is on A. So you have -1 over A, and then changing A over T, that is going to be equals to 1 over D, and then changing D over changing T. So that is the relationship that is there. So that equation you've written is what? An overall equation that is connecting these species. Okay? That is doing what? Connecting these species. Any questions? Any questions?
No, sir, not from me.
Okay, so and then from the rate, we can actually now look at an example, I think, where we are applying the rate to a calculation. Okay, so anyway, before we look at that, okay, so here they're saying the short time period for a crosser concentration over time is the corresponding derivative. So when you're looking at all, what I was trying to explain there is what they've written here. So the rate of the reaction is equals to -1 over T, and then you have this, which is equals to 1 over B, and then you have this, which is equals to 1 over C, and then you have that, which is equals to 1 over D, and then you have this. So overall, I expect when I was explaining, you guys have written something that looks exactly like this. So this is how you calculate the rate of a given reaction. So these variables should not be left out. The coefficients should not be left out. So this is how you do your calculations. And then from here, we go to, so that is an example, and probably they've solved it like that. They are saying, this is the reaction that you have. So consider a specific chemical example for gaseous phase reactions that occur when a mixture of 1 mole of hydrogen and 2 moles of iodine chloride at 230 degrees Celsius in a closed 1 liter vessel. So hydrogen reacting with iodine chloride to give you iodine and hydrochloric acid. This is the reaction. Now look at the way it's happening. 1 mole of hydrogen is reacting with 2 moles of iodine chloride to produce 1 mole of iodine and 2 moles of hydrogen chloride. So what it is here is that if you want to calculate the rate of this equation, you can decide to calculate with respect to any one of these. But whichever you choose, this is how it's going to come out. The rate is going to be equals to negative change in hydrogen over time, because hydrogen does not have a coefficient in front. So you can just write it like that, which is equals to -1 over 2. Since iodine chloride is a reactant, so it has a 2 in front, so 1 over 2 to give you what the rate is going to be, which is equals to, this does not have any coefficient, that is it, that's why it's like that. And then this has a coefficient 2, that is why it is like that. Meaning, if you know the change of any one of these, you can use it to find the rate of any one of these particular reactions. So if you are comparing between this one and this one, all you have to do is get this and equate it to that, and then further go on with your calculations and stuff. That is what the rate actually is. Now, this is just you describing what the rate of the reaction is. So what we've said is that the rate of the reaction is happening as the concentration is changing in a given time. Okay, so the rate is changing in a given time. Now, apart from that, we have what is known as average rate. So the average rate of a reaction over each okay, so what the average rate of the reaction is that it is the overall rate of the reaction. The average rate of the reaction is the overall rate of the reaction, or the overall rate at which a given reaction is taking place. So overall, average is overall. When you measure from your beginning to your end, and then you use the initial concentration and your end concentration, and then the total time under which this reaction has taken place. And then you use these for the calculation. What you're going to get is the average rate of a given reaction. And then we also have what is known as an instantaneous rate of a reaction. An example of an instantaneous rate of a reaction is, say, the reaction you measure at a given time. So say, what is the rate of the reaction at 2 minutes? So you want to find the rate of the reaction here at what? 2 minutes. When you want to find at 2 seconds here, that particular rate of the reaction is going to be considered as the instantaneous rate of the reaction. Okay, so here they're even saying instantaneous rate of the reaction. So if you're doing instantaneous rate, what you're going to do is you find a tangent to that particular curve, and then you are going to do a computation of the gradient to this particular curve. The answer you're going to get is going to be your instantaneous rate of the reaction. Okay, that is what instantaneous rate of the reaction actually is. So there is an example here of a question. At some time, we observe that the reaction of dinitrogen pentoxide produces nitrogen gas and oxygen in forming nitrogen dioxide at a rate of this. So this is the rate at which this reaction is happening. What is the rate at which what is the rate of change of oxygen? Okay, what is the rate of change of oxygen at this particular time? What is the rate of change of dinitrogen pentoxide at this particular time? What is the rate of the reaction at this time? So this is the overall rate of the reaction that has been given here. So your job will be make an equation that equates all these to the rate, and then you will start using that to find in your answer. So you already know rate is equals to, since this one has 2, you're going to say is equals to -1/2, and then you multiply that by the rate of change of dinitrogen pentoxide over